Introduction. It has been an exciting month with the release of breathtaking photos of our universe by the James Webb Space Telescope, JWST. Images such as Webb's first deep field give us a chance to see faint, distant galaxies as they were more than 13 billion years ago. It's the perfect time to step back and appreciate our first-class ticket to the depths of the universe and how these images allow us to look back in time. These images also raise interesting points about how the expansion of the universe factors into the way we calculate distances at a cosmological scale. Looking back in time might sound like a strange concept, but it's what space researchers do every single day. The speed of light. Our universe is bound by the rules of physics, with one of the best-known rules being the speed of light. When we talk about light, we're actually referring to all the wavelengths across the electromagnetic spectrum, which travel at around a whopping 300,000 kilometers per second. Light travels so fast that, in our everyday lives, it appears to be instantaneous. Even at these breakneck speeds, it still takes some time to travel anywhere across the cosmos. When you look at the moon, you actually see it as it was 1.3 seconds ago. It's only a tiny peek back in time, but it's still the past. It's the same with sunlight, except the photons, light particles, emitted from the sun's surface travel just over 8 minutes before they finally reach Earth. The Milky Way and beyond. The Milky Way, our galaxy, spans over 100,000 light-years. The beautiful newborn stars seen in JWST's Carina Nebula image are 7,500 light-years away. In other words, this nebula, as pictured, is from a time roughly 2,000 years earlier than when the first ever writing is thought to have been invented in ancient Mesopotamia. Anytime we look away from Earth, we're looking back in time to how things once were. This is a superpower for astronomers because we can use light, as observed throughout time, to try to puzzle together the mystery of our universe. Space-based telescopes let us see certain ranges of light that are unable to pass through Earth's dense atmosphere. Hubble versus JWST. The Hubble Space Telescope was designed and optimized to use both ultraviolet (UV) and visible parts of the electromagnetic spectrum. The JWST, on the other hand, was designed to use a broad range of infrared light, which is a key reason it can see further back in time than Hubble. Galaxies emit a range of wavelengths on the electromagnetic spectrum, from gamma rays to radio waves and everything in between. All of these give us important information about the different physics occurring in a galaxy. When galaxies are near us, their light hasn't changed much since being emitted, allowing us to probe a vast range of wavelengths. However, with extremely distant galaxies, this is no longer the case. Cosmological redshift. The light from the most distant galaxies, as we see it now, has been stretched to longer and redder wavelengths due to the expansion of the universe. This means some of the light that would have been visible to our eyes when it was first emitted has since lost energy as the universe expanded. It's now in a completely different region of the electromagnetic spectrum. This phenomenon is called cosmological redshift. This is where the JWST truly shines. The broad range of infrared wavelengths detectable by Webb allows it to see galaxies Hubble never could. Combine this capability with Webb's enormous mirror and superb pixel resolution, and you have the most powerful time machine in the known universe. Using the JWST, we will be able to capture extremely distant galaxies as they were only 100 million years after the Big Bang, which happened around 13.8 billion years ago. However, those galaxies are not 13.7 billion light-years away today. The actual distance to those galaxies is about 46 billion light-years due to the expanding universe. Dark energy and expansion. This discrepancy is all thanks to the expanding universe and the mysterious force driving it, known as dark energy. Dark energy is thought to be a universal constant acting equally in all areas of space-time, the fabric of our universe. The more the universe expands, the greater the effect dark energy has on its expansion. This is why, even though the universe is 13.8 billion years old, it's about 93 billion light-years across. We can't see the effect of dark energy on a galactic scale within the Milky Way, but we can observe it over much greater cosmological distances. A remarkable time. We live in a remarkable time of technology. Just 100 years ago, we didn't know there were galaxies outside our own. Now we estimate there are trillions and we are spoiled for choice. For the foreseeable future, the JWST will take us on a journey through space and time each and every week. We have included a link in the description below where you can stay up to date with the latest news as NASA releases it.